revision stream. These are the topics, just to show you again, that we're going to be going through, linked to the mock exam which you have tomorrow. Just some ground rules before we start. You're able to comment on the video as it's live, and the comments, if you ask any questions, we'll try to answer them as quickly as possible. Miss Walker and Dr. Finch are there to write down any questions you have that I can answer. We can go through those. But if the comments are silly, then we will have to delete or even disable the comments function of the live stream. So let's ask sensible questions, and let's all use this to our benefit to actually try and learn something and improve for our mock exam, which is tomorrow. So we do only have half an hour to go through everything, which may seem like a long time, and it will certainly be a long time for me, but in reality, to cover everything that we need to know for the mock exam, it's not going to be an incredible length of time. So we're going to get started, and as I say, we're going to cover these, and we're going to go through in this order. So we're looking at rates of reaction first of all. So rates of reaction is the first topic we're going to cover, and with rates of reaction, the rate of a chemical reaction is just how fast a chemical reaction takes place. And you can actually calculate the speed of a chemical reaction. So if you know a chemical reaction produces a certain amount of gas, so say we produced 100 centimetres cubed of gas, and in that time we did it in 10 seconds, so it took 10 seconds to actually produce that. What we would do to find the rate of that reaction is you take the amount of gas produced and you divide it by the length of time. If you do that, then you will find that the rate is 10 centimetres cubed per second. So we can work out the rate of a chemical reaction. This would be one if gas was given off. There's lots of other ways to measure chemical reactions, but if it was produced in a volume of gas in a set amount of time, we could calculate the rate of that reaction. So that's the overall chemical reaction rate, how fast the chemical reaction takes place, and we can work out how fast that actually is. Things will affect the rate of the chemical reaction, and we should have covered this in year 10, so last year, the factors that affect the rate of a chemical reaction. So, some of the factors are, the first one is temperature. Temperature will affect how fast the chemical reaction takes place. The hotter the temperature, the faster the reaction will take place. The colder the temperature, the slower the reaction will take place. Another thing that affects the rate of a chemical reaction is the surface area. The surface area tells us the amount of surface available for particles to react. So the more surface area they have, the more surface there's available for particles to collide with each other and therefore react. We also have concentration. And concentration affects the rate of reaction by, if we increase the concentration, we will increase the rate of reaction. It's so simple with concentration. Concentration is just the number of particles in an amount of space. So if we were in this classroom that I'm in now, 104, if we had 10 students in here, we all closed our eyes and ran around, we'd bump into each other fairly often. If we had 20 students, we'd bump into each other twice as often. So if you double the concentration, you double the rate of reaction. Okay? And it comes down to collision theory, which we'll go over in a bit. And then last of all, another way, a simple way to speed up a reaction, is to add a catalyst. And by adding a catalyst, it speeds up a reaction because it makes it use less energy. So you need less activation energy for particles to actually react, and hence it speeds up a reaction. A very important thing about a catalyst is it's not changed in a chemical reaction. So by adding a catalyst, it's not changed at all. So catalysts are great because they make a reaction go faster, but they don't change a chemical reaction. Don't change in a chemical reaction, I should say. So those are the four factors which will affect the rate of reaction. If you want to investigate any one of these factors, so if I wanted to investigate how surface area affected rate of reaction, then I would have to keep the temperature, the concentration, and the catalyst, any catalyst that was in there, the same. If I wanted to investigate the surface area, I'd have to keep these other things the same in the reaction. These factors all affect rate of reaction by changing the amount of collisions that particles have. So particles collide all the time. The particles in air are colliding all the time around us. They're not necessarily reacting, but they're always bumping into each other and colliding. If we just look at temperature as an example, if we have particles that are flying around, so they're whizzing about, and there's different particles whizzing about. Every so often these particles are going to bump into each other. They will collide. For a reaction to happen, particles need to collide, but they also need to have enough energy. This is called collision theory. So collision is what leads to a reaction. So for a reaction to occur, particles must collide with enough energy to react. In this, with temperature, we've got two different particles. We've got red and black particles, and they're colliding at a certain speed. If we increase the temperature, what happens? We're supplying more energy. So just like if we supply more energy to a classroom of 5-year-olds, they're going to move about faster. That's the same thing with particles. The more energy you give them, the faster they're going to whiz around. So they're going to be flying around even faster if we give them more energy. And because they don't think, they don't move in set directions, eventually they're going to bump into each other. And the hotter they are, the faster they're moving, the more often, is a key word to say more often, they are going to collide with each other. When they do, they're going to have more energy. So when they have more energy, they're more likely to react. So if you increase the temperature, you're going to increase the rate of reaction because particles will collide more often or more frequently, and they will have more energy when they do collide, and the reactions are more likely to be successful. If we were to show that on a graph would be like this. We'd have along the bottom the time of the reaction. So this would be the length of time along the bottom, and maybe in seconds. And this would be a reaction taking place. So again, if we went with volume of gas produced, it would be volume along here in centimetres cubed. Now, if a reaction was done at 20 degrees Celsius, okay, the reaction might go like this. It'll eventually go flat because all the reactants would be used up. So the reaction wouldn't be able to go any further than that. If we did it again at a colder temperature, so this would be at 20 degrees Celsius, okay? If we did it again colder, so at 10 degrees Celsius, the line would be less steep at a colder temperature. And it would still reach the same height and become level. So this would be at 10 degrees Celsius. If we did the reaction again, but at a hotter temperature, let's say 30 degrees Celsius, the line is going to be steeper. So the line will be steeper, but it will still level out at the same point. So the hotter the temperature, the steeper the line will be. Or if you want to use a key term, it will have a higher gradient. So the higher the temperature, the steeper the line, or the higher gradient. But they will still level out at the same point. They will become level at the same point. So we can conclude that at a hotter temperature, the reaction is taking place faster. Okay? So to recap the factors that would affect it, temperature is a key one because we're increasing the energy of particles. And we increase the speed that they're moving and give them more energy in collision. If we increase the surface area, going back to number 2, okay, we're increasing the amount of surface available for the reaction to happen. So if we increase the surface area, it's like if we got a cube, particles can only react with the outside of them. Okay, whereas if we split that cube up into smaller cubes, okay, the cubes are smaller, but the actual surface that we can collide with has increased because we can react with all of the insides of all of the cubes as well. So by increasing the surface area, we've increased the amount of surface available for collision to take place. If we wanted to test surface area, we'd have to keep the concentration the same, because concentration also affects it. Okay, that affects rate of reaction, and also catalyst as well. We'd have to keep that the same if there was any catalyst in there, because catalyst affects the rate of reaction. So these are all things that can affect the rate of reaction. A catalyst is great because it lowers the amount of energy, and energy costs money. So the lower energy you can do something with, the cheaper it is to do a reaction, which is something companies love and something examiners love. They love asking questions about how companies save money. So that's a really good one. Okay? So that's rates of reaction. Okay, the first topic that we were covering on our little list. Okay, we've gone through the basics of rates of reaction, so we can check that off. Okay, haven't any questions come in specifically about it, so I assume you're all going to get full marks in the mock tomorrow. So I'm looking forward to that. And we're going to move on to the structure of metals, which was the next topic we're going to be covering just in this little session. So, metals, really good substances, because one of their great properties that we know about them is they conduct electricity. Okay, so metals conduct electricity, and it's great that metals conduct electricity because we can use them for things like wires and other good stuff like that. So the structure of metals is one that's very, very simple to learn. Okay, when you're looking at metal structure, the first thing you need to know about it is all the particles are like this. They're all lined up in layers, so it's arranged in layers. Okay, that makes it malleable. It means the layers can actually slide over each other, and you can bend a metal bar because the layers will slide over each other. Okay, that's the first thing about metals. Also, all of these are positively charged ions. Okay, so all the layers are positively charged ions. These are layers of positively charged particles, ions. And in between them, we need something to hold them together. So they actually have, and this is going to be quite small, I apologise this is on the board, but trust me, there are little like dots which are the negative electrons. So, not sure how well you can see that, but these little lines that I've drawn are negatively charged electrons. And those electrons there, they are called free electrons. And because they're free, they're able to move around the whole metal structure. And because they can move, they can carry electricity with them. If ever there's a question, it's number one tip, if ever a question asks, why does a substance conduct electricity? A great answer is these two simple words, free electrons. Okay, if you say free electrons, it's usually maybe 2 marks in an exam. One for saying they're free and one for noting their electrons. So it's a really good exam tip to just pick out that if anything conducts electricity, 80% of the time, maybe even 90%, it's because they've got free electrons. Okay, that's present in there. So to recap, the structure is arranged in layers. It's made up of positively charged ions, okay, which has delocalized electrons. We've had a question come in that's great, that says, what is meant by free? Now, this is a really good question, because another word you can see it called is delocalized. Free means they're free to move. Okay, they're free to move about the room. I can move about here freely. Okay, nothing's stopping me. These electrons can whiz about. They are free to move. Okay, they can sometimes be called delocalized electrons. So instead of free, you can call them delocalized electrons. Okay, so these are free electrons. Okay, they're free to move about. They are able to move over the whole structure. So a great question here, what is meant by free electrons? Electrons that can move about. And because they can move, they can carry electricity. Okay, if I was an electron and this was the metal, this would be the electricity, and I could move about and I could carry it from one end of the metal to the other. Just trying to be careful not to go off screen. Okay, but I can carry this all the way along from one end of the metal to another, pass it along. So electricity can be passed along from one side to another. So this is the structure of a metal and how it's set up and why it conducts electricity. Delocalised, if you're asking what that is the same as free. So delocalised means it's the same as free. It's able to move. So really, if we want to put it up, it means it's able to move. Okay? But really, the key term is free or delocalised. You can use either, even if you're not sure what they are. If something conducts electricity, it's because it's got free electrons in its structure. Okay? So that's metal structure and how they're actually arranged. Okay? So I'm going to bring something in now. Change it. So hopefully, to get rid of some of the glare, I'm going to replace the metal board with this. We can get rid of that one. It's going to fall off the back. Right, so that was delocalised electrons in a metal structure. So that makes it really good. That was the metal structure. Now I'm going to, we can see the metal structure, I'm just going to lift this up quickly, because that's the structure of a normal metal, pure metal. And pure metals are bendy because they have those layers that can slide. Now, in an alloy, okay, which is different, an alloy is arranged in layers, but within those layers, there are big atoms of a different metal or non-metal. Okay? And because it's got these big atoms that are different to the rest of the atoms in the metal, they can't slide. These layers can't slide over each other. So the layers can no longer slide. So this is the layers that would originally be there, and these are the big atoms of a different substance that are stopping the layers sliding over each other. Okay? A question was, what is an alloy? So what is an alloy? An alloy is a substance that's made up of more than one metal, or in some cases it can have a non-metal in the structure, such as iron, which has got carbon in there. So a substance made of a metal plus another metal or another substance. Let's just go another substance for now. As I run out of space, but that does say substance just off the board. With this, okay, the good thing about alloys is they are stronger. Alloys are stronger than just metals, so they are strong. Yeah, that's the good thing about alloys, they are strong. Okay, you can have, for example, like alloy wheels on a bike or alloy wheels on a car. You get that can be much tougher. So they make it out of an alloy because it's much tougher than a pure metal. A pure metal is quite bendy. Okay, iron bars, you could actually, me, because I'm super strong, could bend an iron bar in half. But a steel bar, I'd have real difficulty bending because it's an alloy and it's got atoms of carbon in its structure. Those atoms make it much stronger, but the difficulty with it is because they're stronger, eventually they snap. So it makes it more brittle as well, so it becomes brittle. Okay, so not only is it stronger, but it becomes brittle. And brittle is where it breaks, okay, when it's under pressure. So alloys are great because they have different size atoms in their structure which stop the layers from sliding. So therefore, it makes it stronger, but it does make it more brittle. Okay, so it's stronger, but more brittle because it can't have these layers can't slide. Just like in the pure metal, the layers could slide over each other. An alloy, they can't slide because these big atoms are disrupting the layers or stopping them sliding. Okay? An alloy that you might come across is a smart alloy. So a smart alloy I'll change this pen, it's not working particularly well, but a smart alloy is something that can do a special function. It can change its shape depending on the structure. Okay, so it can change its shape depending on the temperature, sorry. So they can be used for braces. So braces you have in your teeth can be made of a smart metal, and they actually change their structure given the right temperature conditions, because it's slightly warm in your mouth. So what they do is they fit a brace loosely, and then in the temperature of your mouth, they actually like warm up and they change their shape and they pull the teeth into the correct position. It's called a smart alloy, because they remember a certain shape. So they're fitted to a certain shape, and they'll actually change their shape based on the temperature. So they can actually pull teeth into the correct shape. Okay. So recapping, because a question asked why was alloy stronger, and it might have been answered on the comments, but okay, pure metals are too soft. Okay, they don't make many things of pure metal because it's too soft. So for example, a coin wouldn't be made of pure metal because it's too soft, it would be too bendy. So they actually make it out of an alloy, because an alloy stops the layers sliding, therefore makes it much stronger. Okay, so that's why alloys are stronger. Okay. So we've done metal structure. Okay, if you had some questions, we'll see if we can go over some things on metal structures on the comments. But for now, we've done metal structures. I haven't mentioned today anything about polymers, but they are a topic that may come up in structure and properties. Okay, so there could be a question there. But I want to move on to the next topic, which is on our list, because as I said, we don't have loads of time for this session today. Get rid of that, even though I'd only written smart on it, which is not very much, but I'm very wasteful of the resources we've got here in science, clearly. I want to talk about isotopes. And I know with my classes recently, I've been mentioning them a lot, because isotopes are common to chemistry and physics. They come up in both. So isotopes are things that are involved in chemistry because they're to do with atoms and what the structure of an atom is. So hopefully we know what the structure of an atom is. We have particles in the centre which have no charge. Okay, so we have particles in there that have no charge, and we have particles in the centre that have a positive charge. Okay, so we've got 5 positive particles in there. So we've got 5 positive particles in the centre, and then around it we would have, slightly too big so I have to do a shell inside. So, in here we've got 5 positive particles. They are protons. We've got the question, so we've had a question come in, I'll answer in a minute. We've got 5 positive particles, and in this, because we've got the 5 positive particles, we've got 5 negative particles around there as well. Now the positive particles we should recognise as protons. Okay, positive protons. The neutral particles we've got in the nucleus are called neutrons. And the negative particles we've got whizzing around the outside are the electrons. Now, the mass number of an element tells us the number of particles in the nucleus. That is protons and neutrons. So the mass number of an element tells us the number of particles in the nucleus, the protons and the neutrons. All elements have the same number of electrons as they do protons. And I've done this in a very specific way because I said I had 5 protons, so I had to have 5 electrons. Now the way we fill those up is only 2 can go in the first shell. And that meant I had another 3 that had to go in the second shell. I'm sure you could tell me how many would fill this second shell, but that number would be put in the comments. Tell me how many could fill the second shell. And also how many could fill the third shell, if you can do that as well. So second shell has 2, how many would fill, first shell would have 2, how many would fill the second and third shells? So this is an atom, okay, in this would have a mass number of, I've got 6 neutrons. So the mass number of this element would be 11. Okay, so that would be the mass number. because it's got 11 particles in the nucleus. Now, the proton number, the number of protons, that tells me the bottom number, which is called the atomic number, okay, which has got 5 protons in the nucleus. Okay, running short of time, but we may run over a little bit because I want to finish this little bit off as well. So we've got 11 particles in the nucleus made up of protons and neutrons and 5 protons in there. So we could tell what element that would be looking at a periodic table. An isotope. What an isotope is? An isotope is an element with the same number of protons but a different number of neutrons. So it would have a different number of neutrons to this. Okay? A question was asked, why is there only 2 electrons in the first shell? It's all to do with, it's not actually GCSE, you just need to know it's 2, but it's to do with the fact that electrons, being all negative, don't like being close to each other. So only 2 being there, the rest of them repel or push each other away. But that is more A-level, it's a good question though. So with this, with an isotope, we have 5 protons and we have 6 neutrons, so giving us a mass number of 11. Okay? If we were to change that slightly, so if we wanted to change what element we had, this one actually is a boron, but if we wanted to change what element we had, we could actually go and we could actually change the number of neutrons there. So if we still had 5 protons, we would still have an atomic number of 5, but if we made the mass number 12, that would have had to have 7 neutrons in it. Okay, it would be the same element, but it would actually have to have 7 neutrons. Because to find out the number of neutrons, you do the mass number, subtract the atomic number. So 11 take away 5 would give us 6, whereas 12 take away 5 gives us 7. So we can tell they're isotopes. They've got different number of neutrons. They're the same element because they have the same atomic number. Okay? So that's what we can tell about isotopes. Isotopes, the definition is elements with the same number of protons, both 5, but a different number of neutrons. This one has 6 neutrons, this one has 7 neutrons. Okay, so an isotope, same number of protons, different number of neutrons. They both have 5 protons, but this one has 6 neutrons and this one has 7 neutrons. Okay, so that's why we can tell isotopes apart. Okay, and that's what you really need to say when talking about isotopes. Okay, you really need to talk about they have the same number of protons, because the bottom number, the atomic number, will be the same, but a different number of neutrons. And you could even say how many neutrons there were by doing 11 subtract 5 would tell you 6, 12 subtract 5 would tell you 7. Okay. We had a question about the excited state of a particle, but like I say, it's not relevant to isotopes. So, like I say, although it's a good question, potentially, not relevant to isotopes. So I'm going to move on now because we're very, very short time. And there's at least one more thing I'd like to cover before we run out of time. So we did isotopes. Okay, so we can tick that off. Salts and acids, ionic and covalent, the last topics we could cover. Okay, I'm going to make a little call. I'm going to call it and say we're going to do ionic and covalent. So all those who are looking forward to seeing salts and acids, which I know so many of you were, you tuned in just for the salts and acids. We're not going to cover it just now, but any questions about it, try and ask me tomorrow before the exam if you wish. It will come up, or have a look at it yourself. Ionic and covalent is a really important bit. And I want to talk about ionic compounds because ionic compounds are really useful materials. So ionic is when you have a metal element, and we can tell a metal element because it's anything on the, I have to look that way, left side of the periodic table, and it's joined with a non-metal element. Okay, so when a metal is joined with a non-metal, we have an ionic compound. And the structure of an ionic compound is the particles all line up a bit like a metal they're in a regular shape. So you could call a metal a giant lattice. Okay? You could call a metal a giant lattice, and this is a giant lattice as well. The difference being for this is you have positive particles with negative particles in between them. So positive particles with negative particles in between them. And just like in life, okay, for so many of you, opposites attract. We've got the positive with the negative, opposites attract, and it's called electrostatic force. It's the attraction between a positive and negative particle, electrostatic force. Okay, so positives and negatives attract. Question was, what is a giant lattice? Now, a giant lattice just means a lattice is a regular shape. These are regular, like rows and columns. Okay, so a regular shape you've got there. And giant just means it's huge. This goes on for millions and millions of atoms, just all joined together in a massive shape. It makes ionic compounds crystalline and makes them appear crystalline if you look at them under a microscope. Okay, but the structure, the key things are, it is a giant lattice. Okay, it has electrostatic force holding it together. It's made up of positive and negative ions in a joined shape. Okay, so that's ionic compounds. Okay, if you make these ionic compounds, that's their structure, and they're really high melting points and boiling points because they're really, really strong. The electrostatic force holding it together. Last thing I want to talk about then, because we have run a little over, but I want to finish off this bit on covalent, which is a real key bit. Okay, so covalent compounds. And the one we're going to talk about is called simple molecules. And all simple molecules have a low MP and BP. Now MP stands for, some of you might know, melting point, and BP stands for boiling point. So not all covalent compounds, but simple molecules all have a low melting point and boiling point. Okay, and the reason they do is because you've got to remember this: forces in simple covalent are weak. Now that's different to electrostatic force, which is really strong, but in simple molecules, forces are weak. Okay, that's what gives them a low melting point and boiling point. Okay, so that's their structure. The forces between them are weak because they're simple molecules. And when I say simple molecules, I mean covalent. So covalent should have perhaps started with this, is when you've got a non-metal with another non-metal. Now that can be itself. That non-metal and a non-metal joined together could be itself. So an example would be bromine. If you had bromine, okay, joined with another bromine, that's bromine gas. Or bromine is a liquid, one of a few liquids at room temperature. But that's a covalent compound because it's two bromine atoms joined together. Okay, so that would be bromine joined together. And there's a very specific reason why I've drawn it like this. It's because you can actually draw what the bonds are like in it. And never miss out these questions in exams. Okay, these questions that look like this, they want you to do something with it. You're filling in the electronic structure. And what you do is you look at bromine, you look at where it is in the periodic table, and it's in group 7. Now I'm quite low here, I apologise, but that's where I've had to put it, group 7. And what that tells us, that means it's when you've got 7 electrons in the outer shell. So what you do when you do a bonding diagram, okay, is you actually link them together and you fill in the electrons. I'm going to use red crosses for the electrons from this bromine. So I'm only doing the outer electrons. And I can tell it's got 7 outer electrons because it's in group 7. So I've looked at my periodic table, I've seen bromines in group 7, so it's got 7 electrons. All of these elements, like chlorine or iodine, have 7 electrons in their outer shell. So what I do is I'm going to put a cross in this central bit here. And once I've used one cross, it's got 7 electrons in its outer shell. How many has it got left? It would have 6 left over, because 7 take away the 1 gives me 6. So I'm just going to put them around here. Then I'm going to go to the other side. If I go to the other side, and I'm going to use dots for this bromine, this is the same, so it has 7 electrons in its outer shell. So I'm going to put one of the dots in this bit here. And then I'm going to put the other 6 just on the bromine. Now when I look at this diagram, if I cover up this bromine and count all the electrons around that bromine, I've got 1, 2, 3, 4, 5, 6, 7, 8. Now I'm sure you told me that there could be 8 electrons in the outer shell of a second shell, or even a third shell if I had a third shell. Okay? And then similarly, this, if I counted it up, has also got 8 electrons. Okay? Both atoms have 8 electrons, they have a full outer shell, they're happy. That's what makes atoms happy, having a full outer shell. So having 8 electrons makes them happy. Both of these, because they're sharing this electron, have a full outer shell. And that's what covalent bonding is. It's where non-metals and non-metals, or the same non-metal, share electrons. Okay? This is called a dot and cross diagram because it's made up of crosses and dots. Okay? You don't actually in GCSE have to use dots and crosses for it. You could use all crosses or all dots, it's fine. Okay? But make sure you answer those questions. They will always have just the rings there and you have to fill them in. Okay? One very last bit, okay, before we wrap this up. We're already about 7 minutes over, so you've had a good chunk of my time and hopefully it's been helpful. But the last thing we talk about is why don't these covalent compounds made up of non-metal and non-metal conduct electricity? The reason is all the particles in a covalent compound have no electric charge. They don't have any electric charge, so they can't conduct electricity. These ones have positive and negative charges, so if they could move about when they were in a liquid, they could conduct electricity. But I haven't written any positives or negatives on these ones, so these never conduct electricity, because in a covalent compound, none of the particles are charged. They have no charge, therefore they cannot carry electricity. Okay, so that's covalent compounds. Okay, got another question. Are we doing a physics video? It's a good question. We'll see if we like this and I get lots of good feedback and lots of £5 notes find their way to B12. I may consider waiving my usual fee and doing a physics video on a Thursday before the exam, which is Friday. But we'll see. It's down to you guys, really. I hope you found it helpful. Please leave any comments, constructive comments I should say, on how we can improve it and do something better next time. I appreciate it's been quite run through quite rapidly. The reason is we've only had about, well, just over now, half an hour to do it. But when we do the real ones for the real exams, I'll be doing about an hour and a half on this. So it'll be a lot longer and we'll be able to get through a lot more. This one's been quite focused and hopefully helpful. There's some thanks as well. Thanks to Joe for his questions. So, like I say, thanks to you others who I haven't been able to mention, but maybe ask some good questions as well. And definitely well done and good luck tomorrow. So, thanks for watching. And yeah, good luck tomorrow. I'll see you then.